and I've got an example for you from page 637 of the calc book. And before we start off with this example, we're going to talk about when you should use the alternating series test. And compared to some of the other tests, it's quite easy to determine when you should use this test. Basically, you use the alternating series test whenever you have an alternating series, which is pretty basic and makes sense. So an alternating series, as you already know, is when you have alternating signs on the term. So you're having a negative term, then a positive term, then a negative term, then a positive term, and you're adding, then subtracting, then adding, then subtracting, all in one series, and that's an alternating series test. And this is commonly denoted by -1 to some n power, or n plus 1 or n minus 1. It doesn't really matter as long as there's an n in there somewhere. And this shows that with every nth term, with every term of n as you're increasing, you're going to go from +1 to -1 to +1 to -1, which shows that it's alternating. However, it's important to note that there are other ways that this can be denoted. For example, sine and cosine. A good example would be cosine of pi of x. So we already know that cosine of any factor of pi is going to give you 1, but we also know that cosine of any odd factor of pi is going to give you -1, because cosine of pi, for example, is -1, and cosine of 3 pi is -1, and so on. And we also know that cosine of any even factor pi is going to give us a +1. So cosine of 0 is 1, cosine of 2 pi is 1, cosine of 4 pi is 1. And this shows that as n is increasing, as the integers of n are increasing, then we're going to go from positive to positive to negative again, which shows that it's an alternating series. So we have here -1 to the n, which shows that this is an alternating series, and so we know that we can use the alternating series test here. And now that we know that, there are two requirements that we have to make sure are met in order to prove that this series converges. And keep in mind that if any of these two requirements are not met, then the series is going to diverge. So the first requirement is the limit, as n approaches infinity, of a sub n has to equal 0. And we're going to define a sub n as 1 over radical n. Basically, a sub n is always going to be the series without the alternating part of it. So if you take out this -1 to the n, you have 1 over radical n. And that's always going to be what a sub n is going to be. So we have to prove that the limit, as n approaches infinity, of 1 over radical n is 0. So we have 1 over radical n. And as n approaches infinity, we have 1 over radical infinity, which is 1 over infinity, which is 0. So here we've proven that this series goes to 0. Now the second thing we need to prove is the n plus 1 term has to be less than or equal to the nth term. And this is important, and it also makes sense, because what this is saying is that every term has to be smaller than the term before it. And this makes sense because if the alternating series is not decreasing like this and it's actually increasing, then you're going to see that we have terms like 1 minus 2 plus 3 minus 4 plus 5, and it's really wacky, and you're going to see that it actually diverges to infinity or negative infinity. So it's important that we have a decreasing series, and this makes sure that it is decreasing. And keep in mind that you can't prove this with plugging in numbers. You have to actually prove it by plugging in n plus 1 and n in place of n. So to prove it, we're going to do 1 over radical n plus 1. So we just plugged in n plus 1 for n is less than or equal to 1 over radical n. And we have to prove this. And this makes sense, and it can be proved because n plus 1 is always going to be greater than n. So the denominators of this one is always going to be larger than the denominator of this one. And because of that, this fraction is always going to be smaller than this fraction because the numerators are the same. And therefore, we have proven that the n plus 1 term is less than or equal to the nth term always. So we've proven that. So we've proven both of the two requirements, so we can prove that this series converges. But we're not done yet. Now we have to show whether or not this converges absolutely or conditionally. And to do this, we have to look at the absolute value of the alternating series. So the absolute value of -1 to the n over radical n. And that's essentially just n equals 1 to infinity of 1 over radical n. Because this is always going to be 1, but it's going to always be negative or positive or negative or positive. So if you have the absolute value, then you can just make it +1 because it's always going to be, like the magnitude is always going to be 1. So we have 1 over radical n. And if this series converges, then that means that the alternating series will converge absolutely. However, if this series diverges, then the alternating series will converge conditionally. And this one's pretty easy because we can recognize this as a p-series. And p is less than 1. And remember, whenever p is less than or equal to 1, the series diverges. So this series diverges, which means that the alternating series converges conditionally. And there we have an alternating series test.